The process of program development generally requires us to represent the data efficiently and develop a step-by-step procedure that performs a given task and can be used to implement a program. For this, we need to study data structures, and for this, we need to learn about algorithms. Data structures are data representation methods that are used to organize data. So data structures basically provide a way of organizing data so that it can be used effectively by the program. For example, the data structures, arrays, linked list, trees are different ways of representing the data. Array is the simplest data structure in which data is organized in linear order in consecutive memory locations. Linked list is also a linear data structure, but it does not store data in consecutive memory locations. Trees are nonlinear data structures which store elements in hierarchical order. Learning about different data structures is very important because the choice of proper data structure can greatly affect the efficiency of our program. Now let's come to algorithms. An algorithm is a procedure that contains well-defined steps for performing a given task. So basically an algorithm specifies step-by-step instructions for solving a problem or performing a particular task. Algorithms and data structures are closely related. When we implement an algorithm, we have to choose a particular representation of data. That is, we have to decide which data structure to use. And for using data structures, we have to develop efficient algorithms for various operations on these data structures, like sorting, searching, traversal, etc. Now we'll learn more about algorithms. Given a problem, there can be many ways to solve it, and these solutions are in the form of different algorithms. So there can be many algorithms to solve a particular problem. For example, there are many different ways in which data can be sorted. So we have various sorting algorithms. Now, when we have more than one algorithm to choose from, we would obviously like to use the most efficient algorithm or the algorithm that is best suited for our requirement. To decide which algorithm is best for us, we should be able to compare the algorithms and identify the most efficient one. The efficiency of an algorithm mainly depends on these two factors: running time of the algorithm and the memory occupied by it. So an efficient algorithm is one that takes less running time and occupies less memory. There can be other measures of efficiency also, like network usage or disk usage, but these are the two factors which are most important. From these two factors also, we are generally more concerned about the running time of the algorithm. So in the next lecture, we will see how we can compare algorithms based on their running time. There are two ways of measuring running time of an algorithm. One is the experimental or the empirical method, and the other is the analytical method. In the experimental method, we implement the algorithm in a programming language, run it on different inputs, and record the exact running time in time units like microseconds, seconds, or minutes. This approach is not very feasible and it has certain limitations. The first problem with this approach is that we have to implement the algorithm in a particular language and run it on a particular computer. So the running time becomes dependent on the software and hardware used for implementing the algorithm. This can lead to false results. For example, a bad algorithm might take less time than a good algorithm if it is run on a faster computer or is implemented in an efficient language. So if we want to compare two algorithms and find which one is better, then we have to implement both of them using exactly the same software and hardware environment, which might not be possible always. Another problem is that we can run the program for a limited number of inputs only, and we might miss some inputs in which the algorithm behaves differently. So the limited number of inputs on which we run the program might not indicate the proper behavior of the algorithm. The third problem is that this experimental method consumes a lot of time. Some algorithms can take hours or days to execute for a certain input. So in that case, this approach is not feasible. Now, due to these limitations, this experimental approach is not used for measuring running time of algorithms. Instead of this, a theoretical method is used. In this method, we analyze running time of algorithms based on their input size. This is also called asymptotic analysis. In this method, we don't calculate the exact running times and therefore there is no need to run the program. So this approach allows us to analyze the running time of algorithms in a way that is independent of the software and hardware environments. This method also allows us to consider all possible inputs. Now we'll see in detail this analytical method in the next lecture. The running time of an algorithm depends on the size of the input, which is generally denoted by n. This input can mean different things depending on the problem that we are solving. For example, if we are searching or sorting an array, then size of the array is the input size for the algorithm. If the input size is small, then the algorithm will take less time. And if size of input is big, then running time will be more. For example, a sorting algorithm will take less time for sorting 10 numbers and more time for sorting 500 numbers. So as the size of input increases, the running time will also increase. Now suppose the input size of an algorithm doubles. Obviously the running time will also increase. The running time might double or it might quadruple or it can become 20 times or 100 times more. It depends on the algorithm. It is this behavior of an algorithm that is studied in asymptotic analysis. So basically for analyzing an algorithm, we'll study how the running time of the algorithm increases with the increase in input size. If the running time of an algorithm increases very rapidly with the input size, then that algorithm will not be considered an efficient algorithm. So in asymptotic analysis, we don't care about the exact running times. We are just interested in seeing what happens when the input size becomes large. Suppose we have two algorithms, algorithm A and algorithm B for solving a particular problem. When input size is 2, both of them take the same running time. When input size is 4, running time for A is 8 and for B is 16. Then these are the running times for input sizes 7, 100, 1000 and 10,000. We can see that running time of this algorithm B increases very rapidly with input size. So for a bigger input size, this algorithm will take a lot of time. For example, for input size 10,000, A's running time is 20,000 only, while B's running time is 100 million. So if we have to choose between algorithm A and algorithm B, we'll definitely go with this algorithm A because this algorithm B will become very inefficient for larger input. So to determine the efficiency of an algorithm, we have to see how the algorithm behaves when the input size is increased. How the algorithm behaves means how the running time increases with the input size. To find the rate at which the running time increases, we'll use a mathematical tool named Big O notation. So in the next lecture, we'll learn about this Big O notation. Big O is the most commonly used mathematical tool to compare the efficiency of algorithms. It tells us about the asymptotic behavior of a function. That is, how fast a function f of n grows as n becomes large. This big O examines the rate of growth of a function by comparing it with some standard functions whose rate of growth is known. Now let us see the formal definition of this big O notation. F of n is big O of g of n, or we can say that f is order of g if there exist constants c and n naught such that f of n is less than or equal to c times g of n for all n greater than or equal to n naught. Basically, this definition means that this function f will not grow faster than this function g for larger values of n, or we can say that g is an upper bound on function f. Here f is the function whose rate of growth we have to examine and g is the function whose rate of growth we know. Now let us see some examples. Suppose we have this function f equal to 5n plus 4 and we take g equal to n. Now let's check whether we can say that f is order of g. This 5n plus 4 will be order of n if we can find some constants c and n naught such that 5n plus 4 is less than equal to c times n for all n greater than or equal to n naught. This is what the definition says. If we take c equal to 6 and n naught equal to 4, then the definition is satisfied and we can say that f is order of n. These constants are not unique. There can be many more values of c and n naught possible which can be used to show that this 5n plus 4 is order of n. For example, we could take c equal to 10 and n naught equal to 5. These values are not important because we'll just be saying that function f is order of n. Similarly, we can show that these functions are also big O of n. Now suppose we have this function f and we have this function g. By taking appropriate constants, we can show that this function 3n square plus 4n plus 7 is order of n square. Similarly, we can show that these functions are also order of n square. In practice, we will not find the order of a function in this way by taking some values of these constants and then proving this relation true. There are some set of rules derived from this definition which we can use to find order of a function. In the next lecture, we'll see how to do that. Now let's see some functions that are commonly used in place of this function g. We have seen that the rate of growth of a function f is examined by providing an upper bound using the function g. Now for this function g, only some simple functional forms are used. These forms generally contain a single term in n with a coefficient of 1. These are some commonly used functions that are used to provide upper bounds. That is, we'll use these functions in place of function g. These functions are ordered according to their rate of growth in increasing order. So here we have slow growing functions and here down we have faster growing functions. In this table, we have values of some of these functions for different values of n. We can see that some functions grow faster than the others. For example, growth rate of this function n cube is much higher than growth rate of this function n or this function log n. Now suppose we have two functions f1 and f2 where f1 is order of n and f2 is order of n cube. Then we can say that growth rate of this function f2 is more than that of this function f1 because growth rate of this function n cube is more than that of function n. So this is how we can compare two functions using big O. In the next lecture, we will see how to find big O for a function. In this lecture, we will see how to find the big O for a function. Suppose we have this function f and we have to find order of this function. So we have to find a function g such that f of n is big O of g of n. The rules for doing this are simple, but before using those rules, we'll try to understand the logic behind them. When value of n is 10, value of function f is this. Now in this value, contribution of this term 3n square is 84.5%. Contribution of this term 4n is 11.26% and contribution of this constant term 15 is 4%. In this table, we can see the contribution of these three different terms at different values of n. So we can see that as the value of n grows, this term 3n square becomes dominant and this smaller term and this constant become insignificant. This is because n square grows very rapidly. This n grows slowly and this constant doesn't grow at all. In big O analysis, we are concerned with the value of the function as n becomes very large. And with the help of this example, we have seen that when n becomes large, the fastest growing term in the function becomes dominant. And the lower terms and constants become insignificant. So we can just ignore them. So if we have a function that is a sum of different terms, then for finding the big O for that function, we just have to keep the fastest growing term and we can discard all the lower terms and constants. So we got the first rule for finding big O. We have to keep the fastest growing term and discard all the lower terms and constants. Now the second rule is that we can ignore the coefficients of the terms. That is, if a function f is c times function g, where c is a constant, then we can say that f is order of g. For example, if we have this function f equal to 5n square, then we can ignore this coefficient 5 and say that f is order of n square. Similarly here, if we have this function fn is equal to 67n, we can ignore this coefficient 67 and say that fn is order of n. Here is the proof of this rule. You can go through it if you want. In the example that we saw in the previous slide, we had this function f equal to 3n square plus 4n plus 15. Now according to the first rule, we can ignore these two terms. So we are left with only this term. And according to the second rule, we can ignore this coefficient 3 also. And so we can say that this function f is order of n square. Now the next rule is simple. If we have a function f that is constant, then we say that f is order of 1. For example, all these functions are order of 1. This is the proof of this rule. The next rule states that while computing the O notation, base of the logarithm is not important. For example, for both these functions, we'll just say that f is order of log n without specifying any base. Now let us see the reason for this. We know that logarithms with different base are related by a constant factor. This is the constant factor. Big O ignores constants, so that is why there is no need to associate any base with the logarithms while specifying the order of a function. In algorithm analysis, we'll mostly encounter logarithms with base 2. Now we'll take some functions and find big O for them using these rules. We'll use this list to identify the fastest growing term in the function. Now this is a constant function, so it is just order of 1. Now here we have these three terms, n cube, log n and n. So here we have n, here we have log n and here we have n cube. And we can see that this n cube is the fastest growing term in this function. So this function is order of n cube. Now in this function we have log n and this constant term. So n is here and log n is here. So n is the fastest growing term in this function and so this function is order of n. In this function we have n log n and n square. So n log n is here and n square is here. This n square is the fastest growing term. So this function is order of n square. Now in this function we have this log n and n log n. So we have log n here and n log n here. So this n log n is the fastest growing term. So this function is order of n log n. There's no need to specify the base of the logarithm as we have already seen. Now in this function we have n square, n cube and 2 raised to the power n. So we have n here, n square here, n cube here and 2 raised to the power n here. So we can see that this 2 raised to the power n is the fastest growing term. So this function is order of 2 raised to the power n. Now in this function, this 6 raised to the power n is the fastest growing term. So this is order of 6 raised to the power n. Now in this function we have n, 6 raised to the power n and factorial n. And from here we can see that this factorial n is the fastest growing term. So this function is order of factorial n. This is the definition of big O. Here function g is the upper bound for function f. Now there can be many upper bounds for f, which means that for any given function f, there can be many functions g such that f is order of g. For example, if we have a function f equal to 5n square plus 4n plus 8, then according to the rules that we have seen, we can say that f is order of n square. But according to the definition, it is equally correct to say that f is order of n cube, because we can find constant c and n naught such that this definition is satisfied. Similarly, it is correct to say that f is order of n raised to the power 6 or f is order of 2 raised to the power n or order of factorial n or order of any function that has growth rate more than n square. In practice, we need to provide the least upper bound. It is also known as the tight upper bound, and these all are loose upper bounds. So all these statements with loose upper bounds are correct according to the definition, but they are not informative. The statement f is order of g will be informative only when the function g is the smallest possible function that satisfies the definition of big O. So our aim is to always provide the tight upper bound. The method that we saw in the previous lecture for finding big O will always give us the tight upper bound. Now in the next lecture, we will see how to analyze algorithms using big O. We have seen what big O notation is and how to find the order of a function. Now we'll see how we can use big O to analyze the running time of our algorithms. For this, first we have to express the running time of an algorithm as a function of its input size. Suppose this function t represents the running time of our algorithm in terms of n, which is the input size. This is also called the time complexity of the algorithm. After finding this function, the next thing that we have to do is find big O for this function t. Now suppose we have 4 algorithms for solving a problem and we want to compare them. So first we'll find out this function t for all the 4 algorithms. These functions represent the running time of these algorithms in terms of input size n. In the previous lectures, we have seen that if the running time of an algorithm increases very rapidly with the input size, then that algorithm is not efficient as it would take a lot of time for larger inputs. So to compare these algorithms, we actually need to compare the rates at which their running times grow. So basically we have to compare the rate of growth of these functions. For that we have to determine the big O for these functions. We have already seen how to do that. In this function, this n cube is the fastest growing term. So this function is order of n cube. This function is order of n square. This function is order of n. And this function again is order of n square. So based on this analysis, we can say that algorithm C is the best because its rate of growth is the least. These algorithms B and D are both order of n square. So they have same asymptotic behavior. So for comparing algorithms, we have these two steps. We have already seen how to find the big O for a function. Now in the next lecture, we'll see how we can find this function t that represents the running time of the algorithm in terms of its input size n. In this lecture, we'll see how to find the time complexity for an algorithm. Running time of an algorithm will be proportional to the number of primitive operations that are executed during runtime. Some examples of these operations are comparisons, arithmetic operations, assignments, input and output of primary data types. To find function t, we have to express the number of primitive operations executed during runtime in terms of its input size n. Now suppose we have this algorithm that performs some simple operations. Each of these operations will take a certain amount of time depending upon the computer that you're using. Suppose this input takes time C1, this assignment takes time C2, this comparison takes time C3, and this arithmetic operation takes time C4. These constants can be in any unit. Now to calculate the total running time of this algorithm, we have to add the time taken by all these operations. And for that, we have to find the number of times each operation is executed. This input, assignment, and arithmetic operation are executed only one time. This comparison operation is inside this loop, and this loop iterates n times because this variable I goes from 0 to n minus 1. So there are total n iterations of this loop. And so this comparison operation is executed n times. So the total running time for this algorithm will be C1 plus C2 plus C3 into n plus C4. Now we have found this function t that represents the running time in terms of n. So the next step is to find big O for this function. We have seen that while finding big O, we can drop the constants and ignore the coefficients. So we'll drop these constants C1, C2 and C4 and we'll ignore this coefficient C3 and we can say that t is order of n. So in our big O analysis, we can ignore all the system dependent constants and therefore this method allows us to analyze algorithms in a way that is independent of the computer. In asymptotic analysis, we are not interested in how much time an operation takes to execute on a computer. We are interested in how many times that operation is executed. So the exact computation of this function t is not necessary. While writing this function t, we'll be concerned only about those primitive operations whose number depends on input size n. Because these are the operations whose number can increase dramatically with increase in input size. And in asymptotic analysis, we are interested in seeing what happens when input size becomes large. So basically, we have to look for operations that are performed in those loops whose number of iterations depend on n. For example, here in this algorithm, we are interested only in this comparison operation because for large values of n, this will account for most of the running time. In the next lecture, we'll take some examples and find time complexity for them. And while writing time complexity, we'll ignore all those operations which are executed constant number of times. We'll focus only on those operations whose number depends on n. In this lecture, we'll take different algorithms and calculate the time complexity for them. In this algorithm, we'll ignore these assignment and output operations as they are executed only once. They don't depend on n. We can ignore this loop also because it will always iterate 6 times only, no matter what the size of input is. Even when n becomes 1 million, this assignment will be executed 6 times only. Now this loop will execute n minus 2 times because value of I goes from n minus 2 to 1. So this arithmetic operation will execute n minus 2 times. And this loop will iterate n times. So this comparison executes n times. So time complexity is n minus 2 plus n, which is equal to 2n minus 2. We can ignore this coefficient and this constant, and we can say that this algorithm is of order n. Now let's take another algorithm. Here we can ignore this input and output operation and we'll focus on this loop. Let us find out how many times this loop will iterate. If the value of n is 20, I will take these values and so the loop will iterate 5 times. If n is 13, the loop will iterate 4 times. And if n is 6, the loop will iterate 2 times. This number of iterations is given by ceiling of n divided by 4. This is the symbol of ceiling function. Ceiling function of a real number is the least integer greater than or equal to the given number. 20 by 4 is 5 and ceiling of 5 is 5. So we have 5 iterations here. 13 by 4 is 3.25, ceiling of which is 4. So we have 4 iterations. And 6 by 4 is 1.5 and ceiling of 1.5 is 2. So we have 2 iterations here. So this is the time complexity and it is of order n. Now let's consider this loop in which the control variable is incremented by 5 each time. If n is 20, I will take these values, so there will be 4 iterations of the loop. If n is 15, there will be 3 iterations. And if n is 6, there will be 2 iterations. The number of loop iterations in this case is equal to ceiling of n divided by 5. So time complexity is this, which is again of order n. So we can say that the time complexity of loops in which the control variable is incremented or decremented by a constant amount is order of n. Now we'll consider loops in which the control variable is divided or multiplied by a constant in each iteration. Here in this loop, control variable is divided by 2 in each iteration. If value of n is 51, I will take these values and the loop will have total 6 iterations. If n is 20, the loop will have 5 iterations. And if n is 5, the loop will have 3 iterations. The number of iterations of the loop is given by ceiling of log base 2 n. So time complexity is this, and we have seen that there is no need to specify the pace of the logarithm in big O. So we can say that this algorithm is of order log n. Now in this loop, the control variable is multiplied by 2 in each iteration. For these values of n, these are the number of iterations. And this number is again given by ceiling of log base 2 n. So time complexity is this, and this is again of order log n. Instead of this 2, if we divide or multiply this control variable by any other constant, then also the complexity will be order of log n. So in a loop, if the control variable is divided or multiplied by a constant amount, then the time complexity of that loop is order of log n. Now we'll consider nested loops. When we have nested loops, we'll be interested in knowing how many times the innermost loop executes, because the iterations of innermost loop will always be more than those of outer loops. Now in this algorithm, this outer loop executes n times. And for each iteration of this outer loop, this inner loop executes n times. So the total number of times this inner loop executes is equal to n square. The time complexity is equal to n plus n square because this assignment executes n times and this comparison executes n square times. These 3 operations we can ignore. Now this n square is the faster growing term. So we can say that t is order of n square. Now in this algorithm, this outer loop iterates n times. And in each iteration of outer loop, this first inner loop iterates log n times. And this inner loop iterates n times. So total number of iterations of this inner loop is equal to n log n. And the total number of iterations of this inner loop is equal to n square. So this arithmetic operation executes n log n times and this comparison operation executes n square times. And so the time complexity is equal to n log n plus n square, which is order of n square. Now in this algorithm, we have to count the number of times this comparison and this assignment is executed because their number will depend upon n. First, let's see this nested loop structure. This outer loop iterates n times. In each iteration of this outer loop, this inner loop iterates n times. So the total number of iterations of this inner loop is equal to n square. In each iteration of this inner loop, this innermost loop iterates n times. So the total number of iterations of this innermost loop is equal to n square into n, which is n cube. So this comparison operation will be executed total n cube times. Now let's come to this nested loop structure. This outer loop iterates n times, and in each iteration of this outer loop, this inner loop will iterate 10 times. So the total number of iterations of this inner loop is equal to n into 10. So this assignment executes 10 into n times. So the time complexity is n cube plus 10 into n, which is order of n cube. Now we'll see some nested loops in which iterations of inner loop will depend on the index of the outer loop. In these cases, we cannot find the total iterations of the inner loop by just multiplying the iterations of the inner and outer loops. Now here in this example, this outer loop iterates total n times. So these are the n iterations of the outer loop. In first iteration, value of I is 0. In second iteration, I is 1. And in last iteration, value of I will be n minus 1. The number of iterations of this inner loop will depend on the value of I. To count the iterations of this inner loop, let's see what values this variable j will take. In first iteration of this outer loop, j will take only one value, which is 0. So there will be only one iteration of the inner loop. In second iteration, j will take two values, 0 and 1. So there will be two iterations of the inner loop. In third iteration, j will take three values, and so there will be three iterations of the inner loop. In second last iteration, I is n minus 2. So j goes from 0 to n minus 2. These are total n minus 1 values. So the total number of iterations in this case is n minus 1. In last iteration, the value of I is n minus 1. So j goes from 0 to n minus 1. These are total n values. So the number of iterations of the inner loop in this case is equal to n. Now we can add all these values to get the total number of times the inner loop iterates. So here we are adding all these values. This is the sum of n natural numbers, and the formula for summation of n natural numbers is n into n plus 1 by 2. So time complexity is this, and this is order of n square. Now in this algorithm, this outer loop executes total n minus 1 times. And these are the values that I will take in these iterations. Now let's count the number of iterations of this inner loop. For that, we have to see the values of this variable j. In the first iteration of the outer loop, value of I is 0, and these are the values that j will take. So the total number of iterations of the inner loop is n minus 1. In second iteration of the outer loop, inner loop will have total n minus 2 iterations. In third iteration of outer loop, the inner loop will have n minus 3 iterations. In second last iteration of the outer loop, the inner loop will have total 2 iterations. And in the last iteration of outer loop, the inner loop will have only one iteration. So the total number of iterations of this inner loop is equal to this. Now value of this summation is n into n minus 1 by 2. So time complexity is this, and this is order of n square. We'll see this nested loop in selection sort algorithm. Let's take another algorithm. Here this outer loop executes total n minus 1 times. These are the values of x in each iteration of the outer loop. And these are the values that index j of inner loop will take in each iteration of the outer loop. And the number of values that j takes gives us the number of iterations of the inner loop. On adding this, we get this result. So time complexity is this, and this is of order n square. We'll see this nested loop in bubble sort algorithm. Now in this algorithm, there is a function call in this loop. Let's assume that this function is of order log n. So the time complexity is given by n log n, which is order of n log n. Now here in this algorithm, we have an if-else statement. When this algorithm is executed, either this block of code will execute or this block of code will execute. While calculating the time complexity, we consider the block whose order is larger. Now here this block is order of n square and this block is order of n. So we'll consider this if-else statement as order of n square. So time complexity for this algorithm is given by n log n plus n square, which is order of n square. Some algorithms perform the same number of operations every time they are executed. These algorithms are said to take constant time and they are all of order 1. For example, this algorithm is order of 1 because it will always execute constant number of steps whether the input size is 100 or 1 million. The number of steps does not depend on input size n. Some examples of constant time algorithms are a function that prints first element of an array of size n. A function that swaps first and last elements of an array of size n is also an example of order of 1 algorithm. Another example could be a function that returns the size of a stack. These algorithms take the same time irrespective of the size of the input. So these type of algorithms are said to take constant time and have order of 1. We have seen that the running time of an algorithm depends on the input size. But some algorithms might take different running time for different inputs of same size. In these algorithms, the running time depends on the type of input data also. For example, suppose we have an algorithm. These are the different input data sets and all are of size n. The running time taken in all these cases is different. So we can say that behavior of this algorithm depends upon the size of input as well as type of input. For analyzing these type of algorithms, we generally consider three cases: worst case, best case and average case. So we define the time complexity of the algorithm in these three cases. Worst case time complexity gives us a measure of maximum running time that an algorithm will take for input size n. Best case time complexity gives us a measure of minimum running time that an algorithm will take for input size n. And average case time complexity gives us a measure of average running time that an algorithm will take for input size n. In worst case, we consider an input for which the algorithm takes the longest time. This input causes the maximum number of operations to be executed. For example, when we search for an element in an array using linear search, the worst case would be when the element to be searched is at the last place or is not present in the array. In that case, there would be n comparisons. So worst case time complexity of linear search is order of n. In best case, we consider an input for which the algorithm takes the shortest time. So this input causes the minimum number of operations to be executed. In linear search, the best case would be when the element to be searched is present at the first location of the array. In this case, there would be only one comparison. So the best case time complexity of linear search is order of 1. In average case, we consider all possible inputs and compute an average. In this case, we have to assume certain probabilistic distribution for the input data. The most common assumption is that all possible permutations of an input are equally likely. In practice, the worst case analysis is usually done to analyze algorithms because in this case, we get to know the maximum time that the algorithm can take. The actual running time can never be worse than this case. This best case analysis is not very useful as the best cases don't occur very often. This case is not very informative as it gives us just the minimum time that the algorithm can take. And the real running time can be much more than this minimum time. For example, an algorithm that takes some seconds in best case might take days to execute in worst case or average case. This average case analysis is very rarely done because calculating time complexity in average case is generally very difficult. So the worst case analysis is most useful and informative and can be easily done. That's why while analyzing algorithms, we generally consider the worst case. So when we talk about the order of an algorithm, we are talking about the order in the worst case. For example, we'll say that this linear search is order of n, although in best case it is order of 1. So when the case is not specified, the worst case is implied. Suppose we have an algorithm which behaves order of n square in worst case, order of n log n in average case, and order of 1 in best case. So we'll say that algorithm A is order of n square. To be more specific, we can explicitly state the order in these different cases. We have seen that the running time of an algorithm depends on the input size. But some algorithms might take different running time for different inputs of same size. In these algorithms, the running time depends on the type of input data also. For example, suppose we have an algorithm. These are the different input data sets and all are of size n. The running time taken in all these cases is different. So we can say that behavior of this algorithm depends upon the size of input as well as type of input. For analyzing these type of algorithms, we generally consider three cases: worst case, best case, and average case. So we define the time complexity of the algorithm in these three cases. Worst case time complexity gives us a measure of maximum running time that an algorithm will take for input size n. Best case time complexity gives us a measure of minimum running time that an algorithm will take for input size n. And average case time complexity gives us a measure of average running time that an algorithm will take for input size n. In worst case, we consider an input for which the algorithm takes the longest time. This input causes the maximum number of operations to be executed. For example, when we search for an element in an array using linear search, the worst case would be when the element to be searched is at the last place or is not present in the array. In that case, there would be n comparisons. So worst case time complexity of linear search is order of n. In best case, we consider an input for which the algorithm takes the shortest time. So this input causes the minimum number of operations to be executed. In linear search, the best case would be when the element to be searched is present at the first location of the array. In this case, there would be only one comparison. So the best case time complexity of linear search is order of 1. In average case, we consider all possible inputs and compute an average. In this case, we have to assume certain probabilistic distribution for the input data. The most common assumption is that all possible permutations of an input are equally likely. In practice, the worst case analysis is usually done to analyze algorithms, because in this case we get to know the maximum time that the algorithm can take. The actual running time can never be worse than this case. This best case analysis is not very useful as the best cases don't occur very often. This case is not very informative as it gives us just the minimum time that the algorithm can take, and the real running time can be much more than this minimum time. For example, an algorithm that takes some seconds in best case might take days to execute in worst case or average case. This average case analysis is very rarely done because calculating time complexity in average case is generally very difficult. So the worst case analysis is most useful and informative and can be easily done. That's why while analyzing algorithms, we generally consider the worst case. So when we talk about the order of an algorithm, we are talking about the order in the worst case. For example, we'll say that this linear search is order of n, although in best case it is order of 1. So when the case is not specified, the worst case is implied. Suppose we have an algorithm which behaves order of n square in worst case, order of n log n in average case, and order of 1 in best case. So we'll say that algorithm A is order of n square. To be more specific, we can explicitly state the order in these different cases. In this lecture, we'll see some common time complexities of algorithms. If time complexity is order of 1, then we say that the algorithm's running time is constant. In this case, all operations are executed once or only a fixed number of times. Such an algorithm will take same time for any input size. For example, the algorithm for inserting a new element in the beginning of a linked list will take constant time. If time complexity is order of log n, the algorithm is said to be logarithmic. Algorithms that solve problems by dividing into smaller problems have this type of complexity. Such algorithms generally reduce the number of elements to be considered in each step. An example of this type of complexity is binary search algorithm, which is used to search an element in a sorted array. If the time complexity is order of n, the algorithm is said to be linear. This is the case when each element of the input is processed in some way. Here the running time is linearly proportional to n. That is, if the size of input is doubled, then running time will also be doubled. For example, the algorithm that prints all the elements of an array or the algorithm that inserts a new element at the end of a linked list will both take linear time. If time complexity is n log n, then algorithm is said to be linear logarithmic. An example of this type of time complexity is merge sort algorithm. Then if time complexity is order of n square, then algorithm is said to be quadratic. This occurs when an algorithm processes all pairs of input data items. In this case, if n doubles, the runtime will become 4 times. This complexity generally occurs in algorithms that involve nested iterations over the input. Bubble sort and selection sort algorithms have quadratic complexity. If time complexity is order of n cube, then algorithm is said to be cubic. This complexity occurs when algorithm processes all triplets of input data items. An example of this complexity is matrix multiplication. Then if the time complexity is order of n raised to the power k for some constant k, then algorithm is said to be polynomial. And an algorithm is said to be exponential if it has running time of order a raised to the power n, where a is some number more than 1. The runtime for these algorithms increases very rapidly. For example, if we have an algorithm with complexity 2 raised to the power n, then the running time for that algorithm will double with each additional element in the input data. An example of exponential algorithm is the Tower of Hanoi problem. Since running time for these exponential algorithms increases very rapidly, they can be used only for small input size and therefore are not of much practical use. Abstract data type is a mathematical model that defines a data type logically. The definition of an abstract data type specifies a set of data and a set of operations that can be performed on that data. The definition only specifies what operations are to be performed on the data. It does not mention about how these operations will be implemented. So basically, it does not specify how the data will be organized in memory and what algorithms will be used for implementing the operations. The dictionary meaning of abstract is existing as an idea but not having a physical existence. So this abstract data type is only a concept or a theoretical model that gives us an implementation independent view of a data type. Now let's see specifications of some abstract data types. This is the definition of list abstract data type. This is the definition of stack abstract data type. And this is the definition of queue abstract data type. We can see that these definitions only specify the operations that have to be performed. They don't mention how these abstract data types will be represented and how the operations will be carried out. An abstract data type is just a theoretical concept and there can be different ways to implement it. For example, the list abstract data type can be implemented using arrays, single linked list or double linked list. Similarly, stack abstract data type and queue abstract data type can also be implemented using either arrays or linked lists. The different implementations of an abstract data type are compared based on time and space, and the implementation that best suits the requirement of the user is used. For example, if a user wants to use a list in a program, which involves lots of insertions and deletions from the list, then it is better to use the linked list implementation of list, because insertion and deletion in arrays require a lot of movement of data. Now let us compare abstract data types and data structures. Data structure is the physical implementation of abstract data type. Abstract data type is the logical view of data and the operations to manipulate the data, while data structure is the actual representation of the data and the algorithms. So abstract data type is a logical description, while data structure is concrete. So an abstract data type tells us what is to be done and data structure tells us how to do it. We can say that abstract data type is a specification language for data structures. A program that uses a data structure is generally called a client. The specification of abstract data type is called interface. And this interface is the only thing that is visible to the clients who use data structures. The clients have no knowledge of how the data is represented and how the operations are implemented. For example, when we use a built-in type, we only need to know the values that it can take and operations that can be performed on it. We don't need to know how it is implemented. Similarly, if someone wants to use a stack, he can simply use push and pop operations without any knowledge of how they are implemented. The representation or algorithms that implement the stack can be changed, but the client code will not be affected as long as the interface remains the same. For example, if the implementation of stack is changed from array to a linked list, The client program will work in the same way and it need not be changed. This abstraction helps the user of a data structure focus on his program rather than going into the details of the data structure.